It is part 3 of the project Canny edge detection algorithm for color images. The Canny algorithm has 5 steps. Here we'll discuss steps 3, 4, and 5. And also we'll consider what you will do. Here is the third step, edge thinning, non-maximum suppression. As one can see from above figures, some of the edges are thick and others are thin. Let's see figure, the gradient magnitude figure. And some are thick and some are thinner, and over there thin edges. And here the assumption is that the edge center will produce largest gradient magnitude, so that once it is thin, then if we measure along the normal direction of edge, then here the edge center will have largest value in gradient intensity. So we'll try to keep only maximum value, and the non-maximum will be suppressed. That is the idea of making thin edges. Okay. Here the algorithm goes through the gradient intensity metric and find the pixel with the maximum value in the edge normal directions, so that the principle is quite simple here. Okay, that has gradient intensity information, and this is angle information. Now for that one, once it is negative, then we try to add pi. I already explained it, and here once you look at the angle, okay, in that one, so that the theta value is from minus pi to pi. So once it is a negative, then along with that angle, now pi is added, then this is opposite direction. So as far as we are considering edge normal direction, it can be either this direction or that direction. It doesn't matter. So we add pi to consider the opposite direction. Now here, after that, the angle and pi of L is added, and here divided by pi over 4, and we try to get 4, which means integer value, and now we are taking modulo, and with 4, okay, this operation is done because of that. Okay, now so that after adding pi here, the angle is from 0 to pi. Now, so for that one, we want to get direction, but only in pixel we have 45 degree angle. Okay, horizontal direction 45, 90 degree, and that degree. So if you consider, for example, the grid points like that, then only the possibility is horizontal direction 45, 90, 135 degree, like that. So by adding half of pi over 4 and divided by pi over 4, and along with that operation, we try to get here for these 4 angles. And now if we are using another color, then, and the middle of that, each one, and middle of that one, pi of 8 angle, so that this area will assign 0, and also it is a 0, and this portion will be 1, this angle will be 2, this angle range will be 3. So that it is a kind of separating regions into 4. So 0 region, which is around the horizontal region. The angle, the edge normal direction is around the horizontal. And in this case, edge normal direction is about 45 degree. In this case, about vertical direction is about 135 degrees. So once it is 0 around horizontal, then we are trying to get horizontal values and left side, right side of the given point, ij point. And if it is a 45 degree angle, then we are choosing along 45 degree angle A and B. And once it is 2, then in horizontal direction, we are choosing 2 adjacent points. And once it is 135 degree, then we are choosing that directional, the adjacent 2 points. And here, now the current value is larger than maximum of these 2, which means if this is maximum, then we save it, and otherwise, originally it is 0, so it remains 0, not changed. So along with this algorithm, we select only the maximum value. Here, find the pixels with the maximum value in the edge normal direction. That's what this function is doing. That's the result for this, the gradient intensity after passing the program. We see here thin edges here. For that one is now thin here now, right? Okay. In this way, we make the edges thin. So it is a very good algorithm, and non-maximum separation seems working very nicely. Okay. Now we'll go step 4, double threshold. Now we are working on this result. Okay, after the edge is thin, and we now apply double threshold. Double threshold step aims at identifying 3 kinds of pixels: strong, weak, and non-relevant. Strong pixels as pixels of high intensities, and if you are sure that the point must be contributed to the final edge, then we get the pixel as a strong pixel. So basically, along with the high threshold, the strong pixels will have the value larger than or equal to the high threshold. And weak threshold and pixels of mid-range intensities not to be considered as non-relevant for the edge detection. And other pixels are considered as non-relevant for the edge, which means that the intensity is lower than low threshold. So that's the reason we call this part double threshold. Okay, here. In practical implementation, we start with in this way: set high and low threshold, and high threshold is used to identify the strong pixels. Low threshold is used to identify the non-relevant pixels. Once the intensity is lower than low threshold, then we identify the pixels as non-relevant pixels, and we discard them. All pixels have intensity between both thresholds are flagged as weak, and in the fifth step, last step, that is, hysteresis mechanism will help us identify the ones that could be considered as strong and the ones that are considered as non-relevant. Through the last step, we distinguish the weak pixels. Some part of weak pixels will be added to strong ones, and some part will be discarded. Okay, this is the reality in here implementation. It is often the case that you should assign two ratios to set the high threshold and low threshold. For example, you choose high ratio and low ratio in this way, then high threshold is assigned by using the high ratio times maximum value of the gradient intensity. And low threshold is now from high threshold, we multiply here low ratio, and we can set low threshold. By using these two values, you can cut the gradient intensity in 3 parts. Top one is strong pixels, mid one is weak pixels, and the bottom one is non-relevant. So it must be discarded. In order to detect weak edges more effectively, one can employ dynamic variable thresholds. It requires some more research, but here detecting strong pixels is quite easy, and strong edges are easily detected. However, some very important weak edges are not easy to detect. In this case, you have to use dynamic threshold. Right now, this threshold is constant, static, and every year applied the same value, but a dynamic threshold case in region by region, point-wisely, the threshold, high threshold, low threshold will be changing based on the intensity value. I believe that will be much better, but it is beyond of your the class, so that here maybe this one can be considered later on for some students who has strong willingness to do some more work. Okay, here, and once high ratio, low ratio given, then along with that we get high threshold or low threshold. In fact, these two ratios are given as in this example. Then for that image here, thin edge intensity image, now we try to get here strong pixels and weak pixels, and this is combined. Now the final edge will be more or less around there. From weak edges, some point will be added from the last step, hysteresis, and so that the final output will be around there. Now for this current step, you should select high ratio and low ratio appropriately. And also you may have to eliminate isolated pixels from strong pixels, which can be carried out as post-processing. Here, these isolated edges are bothering a little bit, so you have to eliminate those isolated the strong pixels. Okay, the final step, edge tracking by hysteresis. Here we have the edge tracking rule. In this step, And some of weak pixels will be now transformed into strong ones. That is hysteresis. So here, now we'll try to read the rule. The hysteresis consists of transforming weak pixels into strong ones. So some of them will be transformed into strong ones if and only if at least one of 8 surrounding pixels of weak pixel is a strong one. And for selected weak pixel, now you try to search the surrounding 8 pixels, and at least one of these 8 pixels is a strong one, then the current weak pixel must be transformed into strong ones. Right? That's the rule, and you will implement a function for the edge tracking. Okay. Now here are what to do, and first download the model code, and from lecture notes you click this one, then you can download. And you have to complete steps 4 and 5 in color edge.m. For step 4, the major work must be to set appropriately 2 parameters, high ratio and low ratio. For step 5, you have to implement a function named hysteresis, which realizes the edge tracking rule in algorithm P.7, that one. So for this rule, think very creatively and try to get a good function. Okay, that is requiring your innovative idea. Okay, now post-processing, and we add another step. In step 6, implement a trimming function in order to eliminate isolated edge pixels, in fact isolated strong pixels, and or strong pixels of length, for example, less than or equal to 3, and you may you have to design also good algorithm to eliminate here the strong pixels. Once you try to do this one, and if you make a success, then I'll try to give you some extra credit. And single isolated edge pixel elimination is quite simple. However, if you try to measure local length, and local length is less than or equal to 3, and that decision requires some idea. So for this portion, you'll get some extra credit. And run the resulting code of yours to get the edges, and now download some another image and run your code and tune it to get more reliable edges. For tuning, you may try to use here a Gaussian filter with a various sigma rather than the TV denoising. So you can use flexibly image the blur operations. Try various combinations of high ratio and low ratio, and I believe you have to set this ratio depend on images. There's no universal here rule for setting these two ratio. They must be set depend on given image. Okay. Here we have another set of extra credit analysis. For noise reduction, you can employ either the TV denoising model or the built-in function image Gauss field, and along with the sigma, and analyze effect of different choices of parameters and functions on edge detection. So if you can say some tendency or the phenomenon, depending on your choice of functions and parameters, then try to add that finding to your final result, a final report. Then I'll try to give you some extra credit. And here, and another one is new idea for the gradient intensity. Right now, we chose the maximum of RGB gradients, and you can find it from line 21 of Carl H.M. And do you have any idea better than that? So if you test along with some new idea, then also try to add your experience to the final result. Okay. Report what you have done, including newly implemented M files, choices of parameters and functions, and images and their edges. That's what you will do. Okay. Thank you.